Recall the functions are continuous at all points of their domains. That's why the domain is very important. Discontinuities can be classified in three different ways. The first one, a removable discontinuity. In this case, the function at a and the limit of f of x as x approaches a are not the same to begin with, but we can redefine the function at a to be the same as the limit of the function as x approaches a. So this is called the removable discontinuity, and it can be fixed to make it continuous at the point x equals a. For example, you have the limit approaches a certain number, but the function value is defined at different value. So we can remove it to make the function, to redefine the function at the point A to be the same as the limit value. Therefore, the whole is filled and the function becomes continuous. The second case is called a jump discontinuity. In this case, the left-hand side limit is not the same as the right-hand side limit, and we cannot redefine it or make it as the smooth curve. The last one, this is the case that we have the vertical asymptote and the function value approaching to this vertical asymptote. And again, these two graphs cannot be connected. And this one is called infinite discontinuity. Example 3 show that f of x equals x squared minus 14x plus 48 divided by x minus 6 has a removable discontinuity at the point x equals 6. That means the function at 6 can be redefined as at the beginning, the f of 6 not equal to the limit of the function as x approaches 6, or f of x might not be defined to begin with. Let's start it with checking with the function value as 6. Function value as 6, we can do the direct substitution by 6 squared minus 14 times 6 plus 48, or divided by 6 minus 6. As you see, this is undefined. Next, we're going to look for the limit of the function f of x as x approaches 6, or the limit of x squared minus 14x plus 48 divided by x minus 6 as x approaches 6. Since the denominator is 0, we are going to use the factoring to reduce the, or to cancel the 0 denominator. So the numerator can be factored as x minus 8 multiplied by x minus 6 and divided by x minus 6. The factor x minus 6 cancelled. Therefore, we're going to find the limit x minus 8 as x approaches 6. Do the direct substitution, so we get 6 minus 8, or just negative 2. So the function value, or the limit for the f of x as x approaches 6 equals negative 2. But at x equals 6, the function is not defined. So this is the case of the graph has a hole at x equals 6, because the function is not defined, going to be the empty circle, and then keep going with the same value of the limit from the left. So the left-hand limit, the right-hand limit values are the same. Therefore, the limit does exist, but the function is not defined. So we're going to fill in the hole by redefining the function. So at x equals 6, f of x can be redefined as f at 6 equals negative 2. So now the hole is filled. And we call x equals 6 is called a removable discontinuity. this example, we are going to classify the discontinuities in the function f of x as x to the third minus 8x squared plus 12x divided by x times x minus 3 at the points x equals 0 and x equals 3. Let's check one point at a time. So f at 0 equals 0 minus 0 plus 0, and the bottom also 0. So it's undefined at x equals 0. And that would happen the same as the function at 3 because the denominator is 0 as well. Okay, so both of them undefined. Now we're going to check for the limit value as x approaches 0 of x to the third minus 8x to the second plus 12x divided by x times x minus 3. Same strategy. We're going to factor the numerator to get x and multiply by x squared minus 8x plus 12. And we can factor a little bit more of the x squared minus 8x plus 12 to become x minus 6 times x minus 2 and divided by x times x minus 3. We see x and x as a common factor. So limit x minus 6 times x minus 2 divided by x minus 3 is the simplified form of the function. So as x approaches 0, we can plug it in without getting the undefined number or without getting the 0 denominator. Therefore, the value as we replace x with a 0, the limit approaches negative 2 or negative 4, sorry, because the numerator will be negative 6 multiplied by negative 2 divided by negative 3. Therefore, we will get negative 4 as limit value as x is 0. We can find the limit value as x approaches 0. So we can redefine, so at x equals 0, f of x can be redefined as f at 0 equals negative 4. That means x equals 0 is a removable discontinuity. Okay, so next one, for the case that's we look for the limit as x approaches 3, and we just use the same reduced factors form of the function, which is the factor x minus 6 times x minus 2 divided by x minus 3. As you see, this case gonna give us some kind of infinity, either positive or negative infinity. We can analyze it that way by looking at the left-hand side, the right-hand side limits. Okay, so look at two cases. So limit as x approaches 3 negative of x minus 6 times x minus 2 divided by x minus 3. X approaches 3 negative, that means x is slightly less than 3. Slightly less than 3, the denominator gonna be negative quantity with the let's see, less than 3, that's about, like, for example, 2.9999. So subtracted by 3, you're gonna get negative quantity, but very, very small. Okay, very small. And replace the 3 with on the numerator. So we get 3 minus 6 times 3 minus 2, or the numerator will return negative sign for the first term and positive sign for the second term. The denominator is negative term, but very, very small. So overall, the quantity will become positive, but very large, or positive infinity. And we do a similar way for x approaches 3 positive, x minus 6, x minus 2 divided by x minus 3. The denominator gonna be positive quantity but very, very small. And the numerator will return negative sign multiplied by positive sign. Overall quotient will return negative in sign but very large. Even though the two sides are not going to the same direction, but both of them will go to either infinity or negative infinity, or we can say the limit as x approaches 3 doesn't exist. Okay, it does not exist because two directions are not going toward to the same value or same direction. If it doesn't exist, so that means the function not defined, the limit itself, it doesn't exist. So in this case, x um, x equals 3 is not a removable discontinuity. And for how about the second case, if you look at the definition of the discontinuity, if it's not the removable, it's at the jump discontinuity, that means the left hand side not equal to the right hand side, which is the case for this one too. But how about case number 3? It's involving infinite limit. Okay, the difference of B and C, B, the left hand side, the right hand side approaching the real number, the real number. But for part C, which is the third type of the discontinuity, an infinite discontinuity is discontinuity that occurs at the vertical asymptote, which is our case for this example. Then back to the example, x equals 3 is an infinite discontinuity.